Uh,
And I just checked. Top Hat is still running.
okay, good. Thank you, Alexander. Okay, so today I want to take a um, time and this is I notice I've titled this extra lecture number one because this is material that is not going to be on the exam. Um, so before you all log off now, there will be a homework question or two uh, um, on it, right? So I think this is still sort of interesting and important material, but it's a little bit outside of what I think are core the core main concepts. So this is not stuff that's going to be on the exam, right? So you can make a big note of that. I wanted to spend some time with polymers, especially solid polymers, because this is a part of the curriculum that is, I think, a bit lacking, right? We have a good number of students who are interested in polymers. A lot of them are coming from the biomedical side, where the real issue is um, the focus is on soft materials. But structural polymers um, are not as well represented in our curriculum, and those tend to be handled more in chemical engineering. But as material scientists, I think it's important that we at least have a good working familiarity with some of these ideas. So this is material that comes from the first module on thermodynamics review and on heterogeneous stability of heterogeneous materials. The second module that we just finished up, and it really has to do with the thermodynamics of polymers and polymer solutions. And so I wanted to start with just a reminder of this kindergarten polymer structure, right? And I'm not getting into the chemistry of it because, well, as a metallurgist, organic chemistry scares me, right? I'm a metallurgist because I only had to take Orgo 1 instead of Orgo 2, that if I wanted to go on and focus on um, polymers, me and Orgo did not get along well. I think I spent more time studying for that class than I did for everything else the semester combined. Um, and I
I
still felt,
used to be a chemical major, so I took OChem once as a technical elective when I switched majors.
yeah,
Living nightmare.
yeah. It's all memorization until you get to higher levels, right? And I don't do well with rote memorization. I have to understand the mechanism behind things. So me and OChem 1 did not go well, and the thought of taking OChem 2. But anyway, so a kindergarten polymer structure, right? We have to think about these as a long chains of carbon bonds, right? And the basic unit is the sp3 hybridized bond. So there's four, each carbon makes four bonds nominally with two other carbons and two hydrogens, and these bond angles is 109.5 degrees of the tetrahedron. And it's important to remember that these can rotate around the bond, and that they're not perfect linear chains. They branch, and they also have cross-linking, right? So you have this network where the actual distance, the actual amount of chain that you have between these cross-links is much longer than the distance between the cross-links when they're in the physical sense. So that you've got like this network here of this coiled up chain, right? And that gives you extensibility here, right? And we also have to remember that polymers can either be essentially isotropic or unoriented, or they can have an anisotropy to them, right? And essentially have a preferential chain alignment to them, right? And so that's going to give you very different properties, right? And in a mechanical sense, if I pull along this long axis, I'm going to have very different response than if I pull along this short axis, right? So just like crystals, just because a polymer is amorphous doesn't mean that it's isotropic, okay? And polymers can also be crystals, right? So here's maybe a goofy question for you. What's the one crystal structure that polymers can't take? Anyone have any idea? Right, obviously, so this is polyethylene, right? And this is clearly a tetragonal unit cell, right? So we know they can definitely be tetragonal. But what can't they be? Well, there is no pentagonal crystal.
They can't be FCC or BCC, I don't think.
They can't be cubic.
Sorry, no, that's wrong time. Cubic?
They definitely can't be cubic, right? Why can't they be cubic?
I'm going to say because cubic is too close and too interbound together to be a polymer. It doesn't have enough range of motion.
Not quite on the right track there, right? The monomers don't have enough symmetry. That's kind of getting there. The bond length varies, yes, right? Jared's got it, right? So think about it. We've got here on this side of the unit cell, we have the A length, we have carbon bonds, right? The same thing with B, but if this is the tetragonal is the C axis, what is our bonding, right? This is van der Waals interactions. And it's extremely unlikely that the bond length of the van der Waals forces is going to be exactly that of a carbon-carbon covalent bond, right? So it's because we have different bonding in different directions, there's no way that we could have a cubic lattice that arises out of a polymer structure. But because polymers can be crystalline, right, and they usually form these little crystallites by chain folding, that means that polymers have dislocations and other defects, right? And so you normally don't think about polymer deformation occurring by dislocation slip. It really can, especially in things like ultra high molecular weight polyethylene subject to shock loading and things like that, where the deformation is very fast, right? The primary mode is actually dislocation slip, right? Most polymers are semi-crystalline because of this chain folding. So really you have this interlaying amorphous layer with a whole bunch of highly defected crystalline regions, right? So you've got these loops that form, you've got kinks in there. So there's a whole suite of defects that arise in semi-crystalline materials that are just not present in others. And it'd be a really great lecture to really spend some time on these, but unfortunately we don't. What I do want to talk about is the thermodynamics of solid polymers and really the deformation of these, right? So we're all familiar with rubber elasticity, at least the general features of it, right? If I take a rubber band and stretch it, right, I can get a large non-linear but completely reversible deformation, right? So this is elastic, right? Right, there's no hysteresis. I don't lose energy if I stretch a rubber band back and forth, right? If I stretch it and let it go, yes, I've done work to stretch it, but then the rubber band does work on the system to come back, right? And so if we view the system as the rubber band itself, it comes back into the same same configuration. Right now, of course, that's assuming that we don't have any anelastic or viscoelastic deformation that's common in other polymer systems, right? We don't have any creep behavior, right? Everyone is probably familiar that, you know, if you leave your car for several weeks without driving it, your tires will develop temporary flat spots, right? From some viscoelastic and viscoplastic deformation, but those happen on a longer time scale than what we're talking about here, right? So without any kind of cross-linking, the molecules just sort of slide past each other, right? We have only these weak van der Waals interactions holding the two chains together, so they will slide past each other, and that gives us a viscoplastic non-reversible deformation. We need some kind of cross-linking in there to have this nonlinear elastic behavior, right? And so we can actually take some very basic thermodynamic considerations and get an understanding of what's happening here, right? One of the first observations is that unlike in metals or ceramics, there's no really observed change in volume during deformation, right? During an elastic stretch, the volume stays the same. And so that means that the Poisson's ratio has to be about 0.5, right? Or the bulk modulus is really about 4 orders of magnitude than the shear modulus, right? Meaning I need to put a huge pressure on a block of rubber to change the volume, right? So that's why natural or rubber or plastic makes in its fully dense state, makes a really awful cork for a wine bottle, right? Makes a really good temporary stopper for like a test tube or a flask. But for a wine bottle, it makes a horrible cork because the volume remains constant, right? So if you try and force it into the neck of the bottle, if I push on it this way, it's going to want to expand this way because of the Poisson's ratio, and it's going to shatter the neck of the bottle trying to get it in. Natural cork is really interesting because it has a Poisson's ratio of about 0. I can compress it this way and it doesn't expand at all this way. But that's a bit of a divergence. So the main idea behind this large reversible deformation is actually polymers are an entropic spring, right? We have very few configurations at large extensions and many configurations at small extensions, right? So we're going to delve into that deep in a bit and make it a little more clear. So let's just do a really basic thermodynamic analysis, right? So if we start from the first law, right, we have our change in internal energy is equal to our change in heat plus change in work, right? And these are, of course, differential changes. If we assume that our process is reversible, right, our heat is equal to TdS, right, our temperature times our change in entropy, and our work is going to be the external force applied minus the pressure volume work of our system, right? So it's the contribution from these two. we combine it together, and then if we assume a constant temperature, we have our external force has to be our change in internal energy with change in length at constant temperature minus the temperature times our change in entropy, change in length, plus the pressure times the change in volume with change in length, again at constant temperature, right? So this is true for any material, right? So this is the thermodynamics of deformation here. And if we look at the response of a crystal versus a solid polymer, right? So we see for crystal, we have essentially a linear response in the elastic regime. In the polymer, we have this large, right? And if we think about what's happening internally, for a crystal, we're stretching all these bonds, right? So that's clearly if we're changing the bond positions, we're changing the bond energy. So we're changing the internal energy of our system, but we're not altering the configuration at all. So to a first approximation for crystals, the force is due to a change in internal energy, but our entropy stays constant. For a polymer, we're not actually tugging on those carbon-carbon bonds, right? Because remember that the distance between the cross links is much smaller than the actual length of the chain that connects them. So when we pull on a polymer like this, we're just changing the configuration of these chains. These chains are not all pulled tight. So in that case, we're reducing the entropy of this chain network, but we're not changing the internal energy of our system at all, right? And this has some really interesting implications, right? If I pull a metal elastically, does the temperature change? Right? No. Right? But if I pull on a rubber band, the temperature does change, right? And it changes in a way that might not be immediately intuitive. So, you know, try this after the lecture. Take a rubber band, stretch it out, hold it up to your, like your lip, something that's really sensitive to temperature change, and let it compress back, right? Don't snap yourself in the face. And then feel what the temperature changes. Well, guess which way it's going to go first, and then try it. And I think a lot of you may actually, most people tend to get the heat flow backwards. But then once you work through it in your head, it makes sense, right? So if we take a look at our force example, right, and if we say that the change in entropy with length is 0, for crystalline materials, we have the bond stretch plus the pressure volume term gives us our force. If we assume for a polymer that we're just changing the configuration, and we say our change in internal energy is equal to 0, we just have this minus temperature change in entropy with change in length, right? Right, and this is where you can think about if I have a positive tensile force and a reduction of entropy, which direction the temperature needs to go. It's this minus sign here that always gets people wrapped up. But play with it and play with the play with this. In a PhD candidacy exam, I once had a disastrous moment. There's a really smart student, and I asked him to use this understanding, this relationship, to design a rubber band powered refrigerator. and it was just the question came so far out of left field that they just sort of fell apart and then lost their confidence for the rest of the exam and almost ended up failing their PhD candidacy exam. So I don't ask that question anymore.
There's actually a channel on YouTube called Applied Science, which used this phenomenon to make a rubber band refrigerator that actually cooled itself down by, I don't know, 2 or 3 degrees Celsius.
Huh, pretty cool. I just thought that was a theoretical kind of thing. I didn't know anyone was actually crazy enough to try and build one. But anyway, so let's take a look a little bit more here at this rubber stretch, right? And if we take a look at our combined second law, right? du equals dq plus tw, we arrange this for basically plug this back in, and we have FDL plus TDS. Oh shoot, I missed my capital letters here. I tell you what, next year they're going to have perfect notes for all this, because now I'm finding all these errata. Okay, so when we're dealing with polymers, we normally deal with the Helmholtz free energy here instead of Gibbs, at least with deformation. Because for polymers deformation, we have constant volume, but we don't have constant pressure, right? So it makes more sense to formulate things in terms of the Helmholtz free energy rather than the Gibbs free energy. And if we consider a change at constant volume at temperature, we have our change in Helmholtz is du minus TDS, or that our change in Helmholtz energy is the work that we put in. So if we want to cause the force to cause a stretch, right, this is just the algebra. We have our partial derivative change in internal energy with change in length, change in entropy with change in length. We've already shown that we've already suggested that this is 0, but can we show that this change in internal energy is 0 in a different way, right? If we want this to be non-isothermal change, right, we can essentially work through the analysis. We have to apply a Maxwell relation, right? I don't want to go through this all in detail, but we end up with the force is the change in internal energy at constant temperature plus the temperature times the change in force with change in temperature at constant length, right? So this is just basic algebra. And provided you remember your Maxwell relations, that involves the second derivative of your thermodynamic terms, and that the change, we can swap the order in which we do the differentiation to develop these thermodynamic relations. I'm sure Professor Akbar spent a large amount of time going through all these with you. But if we rearrange this for what the change in internal energy with respect to length is, there was some really nice experimental work in 1935 from Meyer and Ferry. And what they did is they pulled a rubber and then changed the temperature and looked at the force required to hold it at a constant length. And they found that this force was linear with the temperature change, right? So that means the change in force with change in temperature is equal to a constant, right? And so if we substitute this in, what we get is we get AT minus, or alpha T minus alpha T, or that the change in internal energy with temperature has to be equal 0, right? So that basically just shows what we had said before, is that the elastic in polymer this elasticity in polymers really arises from the change in entropy, right? And the analysis of this, we're not going to go through it because the mathematics is a bit more complicated than what I want to do. But how do we analyze this in a more sort of applied way, right? So this is a good theory. This gives us a good theory. But now what we need is a model that tells us what the force is going to be as I pull on an actual polymer, right? I need a model that tells me what the response is going to be, that I can use to predict what's going to happen under different situations. And the model that's used is this notion of a freely jointed chain, right? So what we do is we say that atoms are closely packed along the polymer chain. But if we think of this ball and stick model, that there's free rotation around the bond, right? And then we think about this polymer chain as being a random walk through space and calculate the number of configurations possible if I have a starting point at the origin and an ending point at some other point Q, right? And I calculate the probability of all these end-to-end distances. And from that, I can estimate the number of configurations associated with the end-to-end distances. Then all I need to do is figure out, as I stretch my chain, how these end-to-end distances will change. I can look at the change of my probability distributions. I can get a change in my entropy. And from that, I can get a force, right? That's the process. Actually working through it is really complicated. Flory did it, was one of the first people to do it. Flory is like the Gibbs of polymers. Flory was like one of the first really big polymer physicists. In the reading, you read about the Flory-Huggins theory for solutions and blends. Well, he also did mechanics and synthesis and basically anything to do with polymers. Flory did it first. He worked for DuPont in his career, but he first calculated expressions. So this is like the probability of end-to-end lengths, right? And so we assume that the chain statistics is a random walk. And if you do that, you get that the expected distribution follows a Gaussian or normal distribution. And then what you get is you can look at the prediction, right? So these dots are the experimental model. If you assume what Flory did and the distribution ends up being Gaussian, you get a model that works pretty well up to a stretch of extension ratio of 3. So this extension ratio is a 3 times. This means that I have stretched it so it's 3 times its original length, right? So which is pretty good. Once you get beyond there, the end-to-end distances start to deviate from Gaussian, and you need different random walk statistics. And lots of other people have done that, right? This shows the model of James and Guth, which is really complicated. But you can, by following the same statistical analysis and making your random walk be more rigorous, you can actually get really good, a really good response, right? So that's what I wanted to talk about, the thermodynamics of polymer deformation, which goes back to the first part. For Polymer Solutions, this is all about Flory. So polymer blends, I think it makes sense to everybody, right? If I have 2 polymers and I mix them together, what happens? The reason why polymer solutions are important as material scientists is not as immediately apparent, but this is the basic for shellac lacquers and a lot of different types of paints, right? It's really important for processing. So one of the most common ways of making polymers for biological and medical applications is electrospinning, right? So that's where essentially you have a polymer solution that you have a biased charge on it, and you use that to spray the polymer solution, which then evaporates and leaves behind a solid polymer. Filtration and other type of things. Recently, there's been a lot of work looking at solvent processing for polymer solar cells, right? So solution processing of polymers is actually a really important way of processing polymers for a lot of applications. The key idea behind this is, let's start from regular solution theories, but then extend it to consider mixing molecules that are different sizes, right? So Flory and Huggins did this work at about the same time. And what they each independently assume that large molecules can be treated as a chain with linked segments. And what they did is they said, let's make it simple. And we're going to say that each segment isn't a monomer, but that each segment is some link that has the same molar volume as the solvent or the smaller molecule, right? The entropy term becomes really difficult when you think about polymers, right? It's like this snake video game, right? So how can I arrange a chain on a three-dimensional lattice? But I need to make sure that the chain has continuity, right? That all the links are connected and they don't overlap each other. So you can imagine, the difficulty in playing snake when you have a long snake, right? It's the same difficulty in packing polymer blends in solution, right? And so what Flory and Huggins, when they worked through everything, they came up with a form that looks surprisingly like regular solution theory for the entropy term, right? Except instead of activity here, we have volume fraction, right? And this is the number of lattice sites associated with each point, right? And what you end up getting when you think about this is that the combinational entropy of mixing the configurational or combinatorial entropy for mixing small molecules is much larger than for that of a polymer solution. And the entropy, the entropy for a polymer solution is much larger than for polymer blends, right? Because you need to take this continuity into account. There's less ways you can pack a chain in a bucket than water molecules in a bucket, right? And so the implications of this are pretty remarkable, because the entropy term is very small for polymer blends. That means that there isn't a big driving force for mixing in polymers, right? So for polymer blends, we're primarily driven by the enthalpy of mixing, not so much the entropy term, right? So what Flory and Huggins did is they invented this term, which is now called the Flory parameter. Huggins defined it in a slightly different way, but pretty much Flory's notation and ideas have become the de facto standard, because Flory wrote the first really important book on polymer physics. So he used, of course, his own theory and his own notation, and no one talks about really what Huggins did, except in the context of Flory-Huggins theory. But if we go back to our regular solution theory, we had this term epsilon that is the deviation between the bonds. Flory uses that too. Z here is the coordination number, right? And he basically says that heat of mixing can be fit to this form, right? That has this bond deviation term, the Flory-Huggins parameter, and then the volume fraction of the polymer, and the number of lattice sites of the solvent, right? And if we combine that all together, we get an expression for the Gibbs free energy of mixing, right? It's typically normalized, right, by this reference, by a reference volume, right? So it's just a little bit of mathematical rearranging. So they say the reference volume is the molar volume of the solvent molecule. But if we have a polymer blend, the molar volume then becomes the polymer, the volume of one of the polymer links that are in the blend. Right, and what this normalization does is it means that we now have an equation that's equally valid for both polymer solutions and polymer blends. That's written in terms of the volume fraction, not the molar fraction, not the atomic fraction, but the volume fraction of the different components, an interaction term, and these M's, which are the degree of polymerization, or you can think of these as like the molar mass, right? How big each chain is in each of these polymer terms, right? But you end up with something that looks very, very much like regular solution theory with this added Flory constant. Okay, so the Flory parameter is almost universally positive for polymer-polymer interactions, right? So that means the heat of mixing for polymers is positive. So most polymers don't mix, right? Almost all polymers will phase separate, right? You need some kind of additional interaction, such as hydrogen bonding or a block copolymer structure, right? What I mean by block copolymers is where you have a large polymer chain where I have a large number of monomers of one type followed by a large number of monomers of another type, right? So there's actual physical bonding between the two types of polymers so that they can arrange themselves in domains where all of block A forms together and all of block B is together, but because they're all chemically connected, they can't physically separate. So making polymer blends is a real engineering and material science feat because we have this high driving force for separation. But also we have to remember polymers diffuse fairly slowly, right? We have to move these big chains so they can't quite get out of their own way. So we have relatively slow kinetics for separation, right? And this has really big implications for polymer recycling, right? We have to sort by the numbers very carefully because if a little bit of a number 2 gets in with a number 1, right? Then we put it into an extruder and make something out of it. Over time, whatever we made is going to come apart as these polymer blends phase separate, right? So, which is why polymer recycling is really normally not done very well or done very effectively, because it requires way too much intervention to try and sort out the different polymers. So for the last couple minutes, I'm going to probably have to just wrap this up quickly on Friday. But I wanted to take another quick look at the free energy of mixing, right? So this is for a single solution, single component, or a system with complete solubility. Here's the fraction of B, right? And so if we notice locally, if we have these two compositions come together, we can always lower our global free energy by forming a mixture, right? And the thing to know, this Gibbs free energy is always concave up. So anytime we're in a concave up region, and I'm at this composition and this composition, I can always lower my free energy by blending together, right? The opposite of that is going to be true if I'm in a concave up region. If I have a composition here and a composition here, and I have my system come together, I'm on this line. If I try and mix together, I now have a positive heat of mixing, so my Gibbs free energy on mixing has to go up, right? And so that's not going to happen. The other way of looking at it is if I'm in this concave up part, and I'm in a blend and I'm already mixed together, what it means is I can reduce my free energy by phase separating locally into these compositions, right? Globally, the equilibrium is still given by these points, right? But that's a whole system-wide event. If we think about what's happening in some local, tiny, tiny little region, right? I have to move a lot of material, a lot of polymer from where I am, if I'm at composition G0, to get to two regions of composition X1 and X2, right? This involves moving a huge amount of mass over a fairly long distance in a species that diffuses fairly slowly. But locally, I can reduce my local Gibbs free energy, or the Gibbs free energy that my individual chains are feeling, by phase separating into compositions that are not at equilibrium, right? And conversely, if I'm over here, right, I can reduce phase separating, means raising my Gibbs free energy locally, right? So if I'm in this concave up region, I'm essentially metastable, right? And no, this is not on the exam, as I had mentioned before at the beginning of the class, right? This is just really discussion and information. There'll be a homework question on this, but not on the exam. Right. So what you can do if you're over here, locally, if I phase separate, I have to raise my local free energy, right? Given enough time, and I will eventually reach the thermodynamic equilibrium. But what it's going to tell me is that if I'm in this region up here, where my free energy curve is concave down, things are going to happen pretty quickly. I'm going to phase separate into this composition and this composition. But once I hit this concave up region, I need long-range diffusion to take over. And I'm in a place where I need a local increase in Gibbs free energy to reach my minima, to reach my thermodynamic equilibrium. So things are going to happen very slowly here. So we tend to be metastable in the concave up region and unstable in the concave down region, right? And this is the basis for spinodal decomposition, right? So we separate, we're going to phase separate here and be stable here. So if you just indulge me for one more minute, I'll just wrap this up, right? And if we look at this curve, these correspond to the inflection point. So where the second derivative of Gibbs free energy with composition equals 0 are the spinodal points. These minima are often called the binodal points. And in compositions where we're between the spinodal and binodal, we're metastable, and phase transformation is going to happen by nucleation or growth, which we'll talk about when we get to diffusional phase transformations. We have a temperature. As we raise the temperature, we get to a point where the spinodal and binodal lines connect. And if at a temperature above that, we have solubility, complete miscibility above this temperature, right? And if we look at the temperature composition space, this is the one point in the space where the third derivative of the Gibbs free energy with respect to composition equals 0, right? So the critical points of this Gibbs free energy diagram defined our complete equilibrium, our metastable equilibrium, and our critical temperature above which we have complete miscibility, right? And so that's what I wanted to hit for polymers. Sorry, I went 2 minutes over. On Friday, we're going to begin to talk about solidification. And there'll be a new homework assignment posted. So, well, have a good day, everyone. I don't want to sit here and keep yammering on.
Before you leave, I got a quick question.
Sure.
I was doing some of the reading last night in preparation for Friday's quiz, and I was going over the Gibbs paper.
Yeah.
A lot of the equations in the paper reference like a energy change, like as a d epsilon. What does he mean by the epsilon? Is it like Gibbs energy, just internal energy? He says energy, but doesn't clarify what.
It's not really clear, right? So you have to remember that Gibbs wrote that while the field of thermodynamics was still being developed, right? And so it's a little loose about whether that's enthalpy or the Gibbs free energy, depending on the situation, right? So since he introduced those concepts, we've refined the formulation a bit. It's like kind of like reading the early continuum or quantum mechanics work, right? There's a lot of ideas that sort of fell by the wayside as we understood more, right? So it takes a lot of effort to really work through those Gibbs papers and understand how everything that he says there relates to our modern understanding. Okay. So
I'll be honest, thermodynamics has never been my strong suit, and this first few weeks have been a major struggle for me, but
right. So really I don't by assigning that, what I wanted you to get a sense of was how far Gibbs was sort of ahead, right? How revolutionary this paper sort of actually was, and the range of things that he thought about.
It seemed very common sense almost, and yet the way he was talking made it clear that no one else had really considered it yet.
Exactly. Right. And that's really the main points that I wanted everyone to get from that. Right. As a study guide or something like that, it's not a particularly useful thing, but it's really remarkable that he introduced the concept of free energy and the phase rule in the same paper, right? Yeah. So, okay, so Brian had a question. Polymers are stretched, they have no change in internal energy, so how does the temperature change when you stretch, right? It's the change in entropy, right? It's the TS term, right? If my force changes and my entropy change, if entropy changes at constant force, then I have to have a temperature change to keep that same force. Right? And so obviously, if I just hold it at equilibrium and I do it reversibly, then my force is constant, so I have no temperature change. But if I do it in an irreversible manner and I snap the polymer back, I'm changing both the force and the entropy, and they're not changing at identically the same rate, right? So the temperature needs to change to make that equation constant at all time, right? It just has to do with the fact that temperature and entropy are completely linked, right? So the change in entropy is heat over temperature, right? So you think about the macroscopic definition of entropy as well. Essentially, that's one way of thinking of it. The temperature compensates for the entropy change during stretching. And the faster you stretch it, the bigger the temperature change is going to be. Because the more yeah. So it's a really interesting phenomena. So okay, well, have a good one, everybody. And we'll see some of you at office hours, and we'll see the rest of you on Friday.